My pleasure to introduce Daniel Ritchie. Since I like to share my personal anecdotes, I wanted to say that we first met a long time ago when Daniel was undergrad, I think, and I was a postdoc at UC Berkeley. Then Daniel joined Stanford to do his PhD with Patanwan, I believe, on procedural modeling, direct and inverse procedural modeling. And at the time, he was using Monte Carlo, Markov chain Monte Carlo to explore the search space. And quickly, he was one of the first to adopt machine learning to guide the search in this huge space of combinatorial solutions. And he adopted also methodologies from program synthesis under what became known as neurosymbolic programming, which he studied in the context of computer graphics. So Daniel collaborated with several of us, including Niloy, on DSLs for shape modeling. And recently, we started a collaboration on applying these type of tools to sketch-based modeling. But today, I think Daniel will cover a broader scope of how to interact with shapes through abstractions.
Cool. Thanks, Adrian. All right. Mute that. Good. So just a little bit of context setting before I get started. This talk is going to be a lot higher level than the last couple of talks we heard. This is much more of a talk about a vision for a research direction that I hope to convince you is worth pursuing. And I want to set the stage by starting with a quote that I like, which is this one. So, the difficulty of generating images has been overwhelmed by a 5,000-fold improvement in the price/computing performance of computing. What remains hard is modeling. The grand challenges in three-dimensional graphics are to make simple modeling easy and to make complex modeling accessible to far more people. So these words were spoken by Bob Sproul in his keynote at the 1990 ACM SIGGRAPH Symposium on Interactive 3D Graphics and Games. It's a long time ago. If you don't know who Bob Sproul is, and why should you care about what this guy thinks about the topic? He, along with Ivan Sutherland, was one of the inventors of the very first virtual reality head-mounted display back in 1968. So he's been doing this for a long time. Now, I was not in the audience for this keynote. I was 2 years old at the time, so this is not where I first encountered this particular statement. I first encountered it here. This is an excerpt of the introduction from Jerry Talton's thesis. Jerry Talton was a PhD student at Stanford who graduated shortly after I started. He's probably best known in the computer graphics world for his work on metropolis procedural modeling. This is a technique this is a paper that applies techniques from Bayesian statistics to enforce really interesting constraints on the outputs of procedural models. So you can do things like make these trees take the shape of the SIGGRAPH logo. And I found all of this super inspirational when I was a new PhD student, both the sort of motivating framing of Sproul's vision and also the particular work that Jerry was doing. And so I spent a large part of my PhD basically following up on this research. Flash forward 5 years later, here's me in 2016 graduating. This is my PhD thesis, and largely what I was doing was building systems to make the kind of problem that Jerry and others were solving just more efficiently solvable, faster inference techniques. So since then, a lot has happened in the 10 years between when I finished my PhD and where we are now. The single biggest obvious thing that's happened is deep neural networks entered the picture. They kind of started taking over a lot of different research fields, including ours. And these networks got deep enough and big enough, and we started calling them foundation models, or more broadly, just generative AI. And now we have really incredible models like this, like Trellis 2, these things which can take images and produce incredibly detailed, fairly realistic looking 3D objects, which would have been unthinkable a decade ago. So it kind of sounds like Sproul's vision has been realized, where we have these systems where a user can take a very coarse, easy to describe idea, like a rugged brown hiking boot. They can put it through your image generator of choice, like OpenAI Image 2. And then you can put it through one of these image to 3D generative models and get a really nice detailed 3D object out. And you could argue, I think fairly compellingly, that these systems have made simple modeling easy, and they've made complex modeling accessible to way more people than it used to be. So so very nice, great success, right? Like we've done it. Not quite so fast. I think there's something a little bit insidious going on here beneath the surface that I think bears examination. And I want to get at this by asking the question about what language do we use when we motivate the research we're doing in 3D generative modeling. And I'm going to get at this by looking at excerpts from introductions of some papers that are in this space. So I'll start actually with Jerry Talton's Metropolis procedural modeling paper, which I found so inspiring at the start of my PhD. It has this sentence: "Unfortunately, the creation of high-quality 3D models is a notoriously difficult task, often requiring hundreds of hours of skilled labor." Here's another one from a little bit later. "The traditional practice of manual 3D modeling is time-consuming and labor-intensive, and it's not well-suited to scaling to this demand." Or, "While expert artists can author high-fidelity assets, the process is painstakingly slow and expensive." Let's see, "The process of crafting intricate 3D worlds is often hampered by the limitations of existing digital tools, which demand extensive expertise and effort. And the process here is both time-consuming and costly." So if we look at the kind of the key common phrases, common sentiments that these statements contain, things like hundreds of hours of skilled labor, time-consuming and labor-intensive, painstakingly slow and expensive, right? Extensive effort, costly, time-consuming. So really, according to us, it seems, us being the community of computer graphics researchers, 3D modeling is something that's really hard, that takes a lot of time and effort to become skilled at. Even once you've acquired that skill, it takes a lot of time and effort to do, like to actually make a 3D model. Is expensive, and I think the implication here that's sort of implied but not said explicitly is that there's a cost to skilled labor. And also it's painstaking. And I think kind of the implication here is that it's kind of not a very fun or worthwhile activity. And this is something, I've heard this kind of language somewhere else recently. I have to turn on my audio here for a second.
It's not really it takes need to get really good at it.
Okay, the audio is not doing what I was thinking. So let me mute myself. Did I make myself there? Okay.
It's not really enjoying it.
Yeah. Okay. So I don't expect most people to know who this is. This is Mikey Schulman. He is the founder of the music generative AI company Suno. Suno is something that I expect some people in the audience have probably heard of. But if you haven't, you can kind of think of it as sort of like the ChatGPT of music. It's basically a system that kind of lets you prompt your way towards creating songs. You can describe a genre, you can put in lyrics, and it spits out audio for you. And when I first saw this, when I first saw these statements, something to know about me, some of you know this, not others of you might not, is I'm actually an amateur musician myself. Here's a photo of me noodling around on my guitar at home. And I found those statements kind of absurd and honestly a little bit enraging. I am somebody, and I know many other people who are like me, who very much enjoy the process of just fiddling around with musical ideas and just, without any concrete, tangible outcome, without producing a single finished song, I can just enjoy being lost for hours in this process. And I'm not the only one who's been pissed off by things that Mikey Schulman has said. There's actually a lot of of backlash against this company called Suno. People are making merchandise declaring how much they hate it. People are hiring planes to fly over cities with banners declaring how much you should not use this stuff. And I think it's worth asking ourselves, right, if musicians feel this way about this guy's vision for this company, it might be worth asking ourselves, how might 3D modelers feel about statements like these, right? Perhaps unsurprisingly, there's been a lot of backlash from the 3D modeling community to companies introducing generative AI features into their software, companies like Autodesk and Maxon. And there's a lot of reasons for this. There's many reasons for these sentiments. Some people are concerned about the ethics or legality of where these companies are getting their training data from. Some people are worried about these tools eventually taking their jobs from them for those who engage in the practice professionally. Some people just legitimately don't think the outputs of these models are as good as what a person could do. And these are by no means exhaustive. There's lots of reasons why people feel this way. In this talk, I want to focus on one perspective that I think is important for researchers in the field to consider, which I think sometimes goes unsaid or goes unexamined, which is that when we make statements like these, like statements in these papers or that guys like this say in podcast interviews, what we're doing, there's a particular value system that we are espousing. We're basically valuing product and we are devaluing creative process. Basically, these statements imply a value system that basically goes something like this. We should seek to make as much product as possible so we can maximize the revenue derived from selling that product or selling stuff that product gets us. And so in this system, in this value system, the process really should be made as fast and cheap as possible. Right? Ideally, you'd snap your fingers and you'd get the product instantly with no time, no monetary cost. And the corollary of this is that the people who engage in that process are sort of incidental, right? And ideally, you'd actually just eliminate them entirely because, right, they're skilled labor, they cost money. So I think it should go without saying, but I think it's worth stating explicitly that this value system is dehumanizing. This is a value system of capitalists, not creators. And when I say capitalists, I mean VCs, investors, executives, the people whose goal is to make as much money as possible. And I think computer graphics researchers have been a little complicit in promoting this value system, obviously through statements like these, the kind of motivations we claim to have in the research that we're doing. And when I say computer graphics researchers, I'm by no means excluding myself. This is actually taken from one of my papers from a few years ago. So I've been sort of oblivious to the fact that I've been doing this. I think there's a variety of reasons why we've been doing this. One of them, I think, might be that the research agenda in this field kind of seems to have been set recently by a small number of large, very well-resourced corporate research labs, but that's kind of a whole other conversation we could get into. But with this being the state of affairs, it's worth asking, are we okay with the status quo, or do we want to do something different? And when I think about my answer to this question, I think about this part this is on the wall of my office back at Brown University. Not the Eurographics Award, this thing on the right. This is a little poster I have up. This is a quote from a television show that stuck with me for many years. How you get there is the worthier part. And I have that there as a visual reminder I can point to sometimes when I'm talking with students that as awesome as it is to get papers and get publications, the process by which you get to those research results, what you actually do, what you learn about how to ask questions, how to conduct scientific inquiry, how to formulate the right experiments, how to learn from failure, how to grow as a person as well as a scientist, that is in the long run so much more valuable than any individual paper that you get at the end of the day. So really, I think what I'm saying with this poster is that I think process is more valuable than product for researchers. And so if I believe that about the research that I'm doing with my students, I think it would be kind of hypocritical of me not to embrace that value system in the actual technical subject matter of the research that we're doing. So let's take a look at what something different might look like. And since I'm here in the UK, I think it's appropriate that I do so by quoting Monty Python. So why do people engage in creative process? And answering this question, I want to set aside the obvious thing that some people do this professionally, some people receive payment or other material benefits for doing this. Why do we engage in creative process? Well, one of the reasons is that it can be fun and provide and add joy to our lives. Here's somebody on Reddit talking about how much they love creating things and how building things digitally is just as joyful as building things physically, and that they really enjoy the process of figuring out how to make something new, how to put all the pieces together. This is actually a particularly powerful one that I found of someone looking into 3D modeling as a hobby to work on combating their depression. It can be a means of personal expression, of expressing something to the world outwardly about ourselves that is otherwise hidden inside. People talk about this as a means of artistic expression that makes sense to them more than, pencils or paintbrushes. This is a great example that I really like. The Alternative Limb Project. This is a sort of a collective of designers who work with different people with limb differences to try to build prosthetics for them, which are reflective of something the person would like to communicate about themselves, as opposed to just being a kind of generic one-size-fits-all flesh-colored prosthesis. Now we're getting into more abstract stuff, but people find some sense of meaning or purpose or growth or self-actualization in these processes. People talk about how fulfilling it can be to make things in 3D, or how it can really open up your mind and to new possibilities or train your curiosity. People talk about how much they like how it challenges them, or how it, in a very dramatic case, gives them a reason to live, even. And again, this is by no means an exhaustive list, but another reason I think is identity and community, identifying as I am this kind of creator. I am, say, a 3D modeler. I can find other people who identify that way, and we can come together and we can share in what it is that we love about this process. Case in point, many of the comments that I just showed on the previous slide are from the 3D modeling subreddit, which is just an online community of people who practice this craft together. It's not just online communities, there's in-person communities. Many of the student volunteers that we interact with at these SIGGRAPH conferences that we go to think of themselves as 3D artists and build sort of lifelong bonds out of these gatherings. And it's not just professional community. Here's a comment of somebody who finds in 3D modeling, and in this case, 3D fabrication, a way to connect with their family, with their kids, with their nephews, their other young relatives. So again, this is not, I cannot possibly claim that this is an exhaustive list of all the reasons why people do this, but if I try to kind of come up with one word to sum up what it's all about, I might pick fulfillment, right? Something that makes us feel like what we're doing, who we are matters. And so with this in mind, I think in contrast to the dehumanizing perspective that I mentioned before, I think a more human perspective might be, instead of saying, our goal as creative technologists, as researchers, should be to figure out how to make a creative process as efficient as possible so that we can minimize the amount of time a person spends doing it. Maybe we should instead be saying, how do we make this creative process as fulfilling as possible so that however much time a creator chooses to spend doing it feels worthwhile to them, feels like something that they gain some value from in the process of doing it. And so if we look back at this sort of incomplete list of reasons for doing a creative practice, there's a lot of different directions you could explore for how you might try to increase a person's fulfillment with the process. I think only some of which are even the domain of computer science researchers. Basically, not every problem in the world has a technological solution, which I think is a lesson that more technologists really should take to heart. But we have some things we can do as researchers in computer graphics. I think this particular component about how fun or joyful it is to work with these tools, that's something we could look at. And in particular, I think it's worth looking at this now because I think that generative AI, as it exists today, can actually be pretty frustrating and unfun to work with. Here's an example that's a couple years old now, but I still like, which is courtesy of Manish Agarwala, who's a professor at Stanford. He had this blog post, which turned into an ACM Tech Talk called Unpredictable Black Boxes Are Terrible Interfaces. Very to the point title, where he details an experience of working with OpenAI's DALL-E 2 image generator. Again, this is a few years old, of trying to get it to produce an image of Stanford's Memorial Church, which is a very iconic landmark on the Stanford campus, in the style of the movie Blade Runner. And going through this multi-round iterative process where after 17 iterations of prompting and reprompting, he just kind of gave up and couldn't get this thing to make the image that was in his head. Now, I know that DALL-E 2 is very old by today's standards and that modern image generative models are much better at producing high fidelity images than this. In fact, I just tried this exact prompt in the new OpenAI image generator this morning. But I still think they're not meaningfully better at being good interfaces, in the sense that when I input that prompt, I had a particular image in my head. The output that I got was not what I had in my head. And I do not know how exactly to change the prompt to get it closer to what I want, right? There's some inscrutable thing happening in the weights of this network that is not visible to me, and that is frustrating. So in thinking about how to do better than this, there's a framework that there's a couple of frameworks that I think are useful, both of which are kind of borrowed from cognitive psychology. The first one is, this diagram comes from Mihai Csikszentmihalyi's theory of flow, which I think probably everybody has heard about the concept of being in the state of flow. It's sort of like in popular science, but there actually is some research behind it. He has this diagram of when a person is doing something, basically where their sort of emotional experience of that thing based on their skill level and on how difficult that thing is to do, what their emotional state will be. And broadly speaking, I think good interfaces for creative practice, specifically, you want to be somewhere in this half of the design space. And exactly where you are, really, it depends on what the individual user is trying to do. Like if they just kind of want to relax, great. If they want a really intense challenge, maybe you want to be up here. Probably most of the time you want to be in one of these parts of the space. And that's why people talk so much about flow, right? Really just getting lost in something where you're really in the zone. You feel like you're just firing on all cylinders. You're making progress, but you also feel like it's easy. Things are not, you're not coming up against roadblocks, and you feel kind of like you have a superpower, and the minutes just fly by. So how do we do that? How do we build systems that get us into this particular part of this design space? For this, I think it's useful to look at another framework from cognitive psychology. This one courtesy of Don Norman, who is kind of a design guru and very, very well known in the human-computer interaction community. He has this theory of when people are working, when users are working with systems, there are these gaps, or he calls them gulfs, that you have to be able to close. One is the gulf of execution, basically figuring out how to do a particular thing in the system. And then the gulf of evaluation, when you took an action in the system, figuring out what happened and is that thing that happened what you actually wanted. And basically the process of using the system is just repeating this loop over and over again of figuring out how to do something, doing it, and evaluating whether it accomplished your goal. And generally speaking, the smaller this gulf is, we can argue the better the interface is for a particular user. They're going to be able to get into a state of flow. They're going to have a more fulfilling experience using the system. So how do we go about building interfaces that do this? Well, what are interfaces made of? Interface is defined by its abstractions. I think probably everybody here is a programmer to some extent. So you can think about this in terms of like object-oriented programming interfaces, right? They provide some set of abstractions. They provide some abstract functions or methods that they can do. And similarly, these creativity support tools provide operations, tools, metaphors, affordances, whatever you want to call them, kind of the atomic stuff you can do in these tools. And different tasks or different users benefit from different abstractions. Not all 3D modeling tasks should use the same abstractions. So very obvious example here is if I'm someone who's trying to build mechanical parts for a car, for example, I probably want to use a CAD tool like Onshape because it provides really precise curve drawing. It allows me to define constraints between elements of those curves. It allows me to do operations like Booleans or chamfer or bevel, things that reflect the physical manufacturing processes that are going to build this geometry. But if I am a 3D artist who's trying to model alien creatures, there's very different abstractions that are going to be useful to me. I might prefer to use something like ZBrush, which is a digital sculpting tool, because it provides abstractions that let me sort of push and pull at the surface to smooth things out, to apply vector displacement maps to add local details to things. These are the operations that I care about. Now, a less obvious, a more nuanced example, even if we're talking about different people working on, we'll call them CAD domains, there's different kinds of CAD tools that would be useful for different people. So if I'm an architect who's trying to design a building, I might prefer a tool like Rhino, which has really mature tools for working with NURB surfaces to make interesting freeform architecture. It has really nice built-in procedural modeling tools for defining the repetitive elements that often feature in building architecture. And it has built-in analytical tools for things like structural analysis, energy usage analysis, how much daylight I'm going to get out of the structure. Now, if I'm a jeweler who's trying to design rings, for example, I'm still going to want to use CAD. This is still something that's going to be a product that's designed to be built in the physical world. But I could use Rhino, but I might want to use a different tool, like this thing called Matrix Gold, which I only know about because the jeweler who made my wedding ring happened to be using it. And I asked him, what is this 3D modeling software I've never seen that's up on your desktop? And this thing is, well, it's a jewelry-specific CAD tool. It has abstractions for gem setting and placement. It has nice features for built-in instantiating objects along surfaces, which is a thing you often want to do in jewelry. And it has a really quite exhaustive library of parametric ring shapes, which makes it really easy to explore different variations of a design without having to build all of those ring shapes from scratch. Okay. So with this in mind, I think here is a goal that I think is worth chasing, right? Instead of doing what all of the developers of all these tools I just mentioned did, which is to hand design all these abstractions for different modeling tasks and different users, and instead of doing what the kind of zeitgeist of the research field at the moment is to do, which is use Gen AI models to synthesize creative outputs, to synthesize 3D models directly, how about we try to build systems that synthesize the right abstractions for each creator's process? Basically, generate the tools that are going to make sense for that individual user for the thing that they want to do. And by the way, in framing this sort of second one as a thing we don't want to do, I'm not saying that we shouldn't use big Gen AI foundation models at all. In fact, I think we actually can use them to help synthesize the right abstractions. And the fact that these tools exist now, I think, is why it's actually possible to investigate this question today. This isn't something that is a question you even really could have productively asked even a decade ago. Okay, so I don't think that this is an aspirational goal. I don't think there's any research right now that quite lives up to it, but I think there's some research that's on the right track. What I'm about to discuss is by no means an exhaustive list, but some things that I think are on the tip of my tongue. One of them is this thing I'll call semantic similarity handles, something called transient widgets, and something we're probably all a little bit more familiar with, procedural abstractions. So semantic similarity handles, this is an abstraction that basically provides a little handle that lets you control how much like X an object is for different values of X. X could be a noun, it could be a type of object, it could be an adjective. And this is by no means a new idea. I think the first time I ever saw this was over 10 years ago, this paper by Urson Umer and Sid Chowdhury and others, semantic shape editing using deformation handles, where they built a system where you could take an object, and they had a predefined set of axes that were quite abstract by that time standards, like how feminine a shoe was, and you could drag along the slider. This image is only showing a set of discrete steps, but this is actually a continuous deformation space, and you can actually vary the design along that axis. There's another example. It's actually even a little bit older, which is doing discrete variation of parts. And I like this. I'm going to play this little video. I like it because it also explains a little bit about how the system works. Okay, so what's changed in the intervening decades since that work was done? Well, at the time, as that video just mentioned, these methods were, the way they worked is that they learned from large data sets of human pairwise comparisons of these different semantic attributes. And that's not something you can do at runtime if your user comes along and says, hey, this is the semantic axis that matters to me. Nowadays, we can replace some of these bespoke data sets that were gathered with large foundation model priors. And in principle, this enables kind of on-demand synthesis of exactly the semantic similarity handles that a particular user cares about. An example of this idea put into practice is, I'm going to highlight some work done by Adriana and her student Milan, which the system reparam CAD, where you can take a 3D shape that is expressed, going to be expressed in terms of a very, very low-level parameterization. In this case, it's just a bunch of cuboids put together. And their system takes this information as input and produces a set of sliders that allow you to control how like a certain type of chair this chair actually becomes. So you can say, I want this to look more like a bench, right? I want this to look more like a stool or less like a stool. I don't have time to get into the nitty-gritty of how it works, but basically, there's a large language model which suggests what semantic axes might be relevant for this shape. And this is something that in principle a user could also provide, or at least edit the outputs of the LLM. There's an image-to-image diffusion model, which takes this a rendering of this input shape and tries to imagine what it would look like in the style of each of these different axes. And there's some differentiable rendering, which tries to optimize the low-level parameters of the original model to make it match those imagined renderings by the diffusion model. There's some more technical details to then convert those parameterizations into these sliders. You'll have to take a look at the paper for that, but that's sort of the high-level idea. Okay. Now, transient widgets, slightly different idea. The idea here is it's an abstraction that provides some widget or some kind of controller that lets you accomplish a very specific edit in the context of the current shape you're working with. And this is a controller that might only make sense or might only be valid with the shape the way that it is. And as soon as you perform that edit, it might no longer be valid anymore. But it's like a hyper-specialized bespoke widget for a specific thing you want to do at this exact instant. OK, very, very abstract. Let's make it a little bit more concrete. So the first instance of anything like this that I can think of is not actually from a piece of like CS technical research. It's from this sort of thought experiment, I guess, by George Steiny, who's an MIT architecture professor, also happens to be the co-inventor of shape grammars, which we use all the time now in procedural modeling. And he posed this question: can you convert the left shape into the right shape using only 2 edits? And initially, you're like, aha, I can do it in 1 edit. That's just a reflection. That's very easy. But then he says, no, the only allowed edit type is translating a triangle. That's the only thing you can do. And you stare at this for a minute and you're like, well, OK, I clearly can't do it by just translating this triangle because that triangle's orientation is reversed. And even if I get clever and think about splitting this little arrow shape into 2 triangles, I still can't think of a way to do it. And the trick is to do this, is to basically shift this triangle over until you get the star shape, and to recognize that in this particular configuration, this new triangle now exists, and now you can move this thing off to the side. And so the key idea here is that the potential representations of a shape change as the shape itself changes. And if the potential representations change, then the stuff you can do with that representation might also change. So certain manipulations are very, very context specific to what that shape actually looks like. So Gilbert Bernstein and Will Lee back in 2015 were also aware of the fact that different representations afford different edits when they proposed this paper called Lilicon, which as far as I know is the origin of the term transient widget. But the idea here was that, well, if I have this like black and white 2D vector art of a little icon, maybe this is supposed to represent a window. If I represent that as 4 quadrilaterals, it's easy to do this edit. But if I represent it as this trapezoid with these sort of strips Booleaned out from it, it's much easier to say adjust the white space that's kind of in between those window panes. And so they built a system which let you do this. You could actually take just any old black and white SVG image, and you could interpret the negative space between parts of the graphic as a stroke, as an actual stroke, and you could adjust that stroke's width and things like that. Super cool. I think this is a paper that's underappreciated, in my opinion. So what's changed since then? So at the time, like when this Lilicon paper came out, these transient widgets were very carefully designed for each individual design domain. It took very brilliant researchers a while to figure this out. Nowadays, in principle, these generative AI models can just do on-demand synthesis of the kinds of user-requested transient widgets you might like. So here's an example of this idea from one of my own papers. This is my student Aditya. We presented this paper at SIGGRAPH Asia a couple of years ago. You could take a 3D model of a chair and you could say, OK, system, give me a widget to adjust the width of this chair. And our system called Parcel would take those instructions as input, and it would produce this little widget, has a slider, and it would adjust the width of the chair, including all the secondary effects that you might care about, like changing the number of slats in the back. And the way that this thing works under the hood is it produces this little program, which has this single degree of freedom X. And all of this text of the program is manipulating different parts of the shape as a function of this value X, the slider value. The way this works under the hood, there's a large language model, which does some stuff. It kind of synthesizes like, what's the initial part that I should transform? Maybe I should adjust the width of the seat. It kind of suggests which transforms are allowed, what relationships between parts maybe should or should not be broken in order to enforce this edit. There's a little bit of geometry, and there's also a computer algebra system that sort of solves for edits that maintain relationships under all values of X. So it's an interesting little piece of work. And last but not least, procedural abstractions. I think we probably all know these fairly well, but the idea is we can represent a shape with a parameterized procedural program which generates that shape. But critically, that program should be decomposed into meaningful, reusable subroutines, things that expose parameters that make sense to the user and that they can use over and over again in different contexts. So there's too much foundational work in procedural modeling to really cite it all, but some of the most important ones that immediately come to mind, Pascal Miller's work on procedural modeling of buildings, defined abstractions like subdividing a volume or repeating some pattern along the face of a volume. Gtangle is a more recent paper that I really like from Fabio Pellicini's lab, which allows the definition of really cool, these called tangle patterns that look like this. And we had some work in my group on a domain-specific language called shape assembly, which lets you define the connected structure of parts in 3D objects. And again, what's changed since these works is all of that stuff in the past, the libraries of subroutines that these procedural models were using were all written by hand. And as I'm sure most people in the audience now know, LLMs are getting pretty good at writing code. And so in principle, they can synthesize these user-requested subroutines. So an example of this is a paper that we haven't yet published, but will be out soon. A paper called ShapeLib that's done by my former student, Kenny Jones, in collaboration with Niloy and others. Here, a user has a certain kind of abstraction in mind, like they want to be able to decompose chairs in a certain way. They can describe what functions they would like. They can provide a small set of 3D objects in which those kinds of abstractions would be useful. And then the system goes ahead and just generates a library of these procedural subroutines, which implements the functions they've asked for. And the way this works is the large language model generates these implementations, but as we know, LLMs hallucinate and they're not amazing at 3D spatial reasoning. So we actually use some geometric reconstruction checks to verify that the implementations that it came up with are actually capable of reproducing the geometric patterns that we see in the small set of examples that were given. It's kind of like our library of test cases, if you will. And when you have these abstractions, in our particular case, the programs themselves only generate assemblies of boxes, but those are already very useful as parametric deformation cages. So you can manipulate the parameters of these programs, and you can use that to control the deformation of some more detailed mesh. Or you could even use this as a sort of a control signal for 3D generators, add detail, and you could explore different detailizations of the structure. Okay, so just to wrap up here, I think what's coming next, I think a long-term goal that's worth chasing is, can we develop technology that lets creators specify their own bespoke modeling system for whatever thing they want to make? If I'm a game designer who's exploring spaceship designs, how can I very easily create my custom one-off modeling tool that lets me do this? Or if I'm a photographer who wants to design and 3D print parts for my camera, or if I'm a parent who wants to make toys for my kid. And I think the idea is that all of these systems, they should provide abstractions that align with how each individual user is thinking about their craft based on the way their brain works, what their expertise level is. I think that's the tricky bit. So, okay, I know I'm over time. I want to wrap up. What I hope you take away from this talk, kind of take-home messages, is I think creative process has at least as much value as product. I think that's something that goes unsaid and overlooked too often. I think that academic researchers are in a fairly unique position to try to develop technology that helps make creative process more fulfilling if we explicitly identify that as a goal. I think to build that kind of technology, it helps to view creative process through the lens of the abstractions that it provides. We're all very comfortable doing that as computer scientists, right? We think about abstractions a lot. And so I think that synthesizing user-specific abstractions, how to do that, is an important research agenda that I intend to pursue, and I hope more people will pursue with me. So to wrap up, I just want to give some acknowledgements about kind of what helped me formulate my thinking in this area. The first person I'll thank is Takeo Igarashi, who hopefully most people know of as kind of a pioneer of sketch-based modeling. He gave a talk recently at the WIST 2025 conference called Easy and Fast, Rethinking the Future of Content Creation Tools. The slides for this are online. I had a conversation with him at SIGGRAPH when he was figuring out this talk, and that was really formative to some of the ideas that I talked about today. And the other person I will thank is Adam Neely, who's a YouTuber. Some of you might know if you follow music YouTubers. But his video, Suno AI Music and the Bad Future, is where I first encountered Mikey Schulman, and also was formative to a lot of the thinking I've shared here. If you don't mind a 90-minute video essay, I actually highly recommend this one as well. So thanks. Do we have any time for questions? I know I went over, so.